Hello, welcome to this video on data flow analysis, one of the most powerful and foundational techniques in compiler design. In next 7 to 8 minutes, we will explore what DFA actually is, look at the mathematical frameworks that make it work, and see how compiler uses it silently make our program faster without us writing a single line of extra code. You can see 7 item agendas numbered from 0 to 7. And the first one is Introduction to DFA. Second is key concept, CFG, Jenkins lattices, DFA frameworks and algorithms, optimization applications, and the worked examples, reaching definitions, advanced optimization, real world impact, and summary. Here's a roadmap for today. We'll start from the very basics. What is data flow analysis and why do we care? Then move into formal frameworks, control flow graphs, gen and kill sets, and lattices theory. From there, we will see exactly how these frameworks power 6 major compiler optimizations. We will then walk through a concrete worked example so that math becomes tangible, look at more advanced uses like register allocation and SSF form, and close with real world impact. First, what is data flow analysis? DFA is a static program analysis technique that gathers info about how data values propagates through a CFG. Three property cards are static, global, and iterative. Why does it matter? So, what actually is data flow analysis? As its core, DFA is a compile time technique, meaning no program actually runs. The compiler reads your source code, builds an internal graph representation, and mathematically reasons about what value flow here, where. It has three defining properties. First, it's static, no execution required, everything happens at compile time. Second is global, it looks at entire program, not just one line at a time. And third is iterative, it keeps reevaluating until it reaches a stable answer, called a fixed point. Why does this matter? Because DFA is the engine behind a dead code elimination, removing code that can never affect output, constant propagation, replacing variables with their known values, and loop invariant code motion, pulling repeated calculation out of loops. All of this happens automatically. Core concepts CFG, Jenkins, and lattices. Before we can run DFA, we need three mathematical building blocks. The first one is control flow graph or CFG. This is how the compiler represents program structure. Each node is a basic block, a straight line sequence of instruction with no branches inside it. Edges represent control flow. An edge from B1 to B2 mean execution can go from block 1 to block 2. The second building block is gen and kill sets. For each basic block B, gen B captures the facts that the block generates or creates, like a new variable definition. Kill B captures the facts it destroy or overrides. In B is what's true when we enter the block. Out B is what's true when we leave. The transfer function ties together. Out B equals gen B union in B minus kill B. In plain English, what leaves a block is what was generated in it, plus whatever came in it that was killed. That wasn't killed, sorry. The third concept is meet operator, which combines facts from multiple predecessors block. For forward analysis using intersection, a fact must be true on all paths to be considered true at a join point. All of this sits on mathematical structure called a semi-lattice, a partial order guaranteeing the algorithm always converges. Equation is out B equal to gen B union in B minus kill B. Worklist algorithm. Now let's see how DFA is actually implemented. There are 4 classic problems every compiler student learns. Reaching definition asks which variable assignment might reach a given point. It's a forward analysis using union as the meet operator. Like variable analysis asks, is this variable value still needed somewhere at after this point? It runs backward through the CFG, also using union. Available expression asks, has this expression already been computed and are its operands still unchanged? Forward analysis, but using intersection. An expression is only available if it was computed on every path to this point. Very busy expression asks the symmetric question. Will this expression definitely be computed on every path from here? Backward with intersection. All 4 are solved by worklist algorithm. Initialize all out set to empty. Put all blocks in worklist. Then repeatedly pick a block. Recompute it in from its predecessor. Apply the transfer function to get a new out. And if anything changed, add successor back to the worklist. Repeat until the worklist is empty. That's your fixed point. The complexity is big of n times d times f, where n is number of nodes, d is the depth of the graph measured by the black edge, and f is the cost of the one transfer function application. For practical programs, this is very fast. Here's where DFA pays off. Let's walk through six major optimizations, each powered by different DFA results. Constant propagation uses reaching definitions. If every definition that reaches a use of variable a assigns the same constant value, says 5, the compiler replaces all uses of a with 5, so b equal to a plus 3, and becomes b equal to 8 at compile time. No runtime calculation here. Dead code elimination uses live variable analysis. If a variable is assigned but is never live, meaning its values is never used on any subsequent path, that assignment is dead and can be deleted entirely. In the example on screen, x equal to 10 is never read before the function returns. So the compiler removes it. Common sub-expression elimination, or CSE, uses available expressions. If the expression a plus b was computed earlier and neither a nor b has been modified since, the compiler reuses the earlier result instead of computing it again. Loop invariant code motion, or LSM, combines reaching definition with dominator analysis. If a cross b plus c is computed inside a loop, but its operand never changes within the loop, the compiler hoists its out to before the loop, computing it once instead of on every iteration. Copy propagation tracks copy assignments like x equal to y. It replaces downstream uses of x with y, enabling further optimizations like another round of dead code elimination. Finally, partial redundancy elimination generalizes both CSC and LICM using a technique called lazy code motion. It handles cases where a computation is redundant and on some path but not all, inserting it on the non-redundant path to make it fully redundant everywhere, then removing it. A correct example of reaching definitions. Here's our program. We have 5 definition points, D1 through D5, blocks B1 executes D1 and D2. Then there's a conditional. If B is greater than 5, we go to block 2, which reassigns A via D3. Either way, we reach block 3, which computes D4 and D5. We build our gen and kill sets. Blocks B1 generates D1 and D2. It kills D3 and D5 because B1 contains definitions of A and B that overwrite later ones, and so on for each block. Now we run the work list algorithm. Start with all out set empties. In pass 1, we propagate forward. B1's out becomes D1 and D2. B2's in is D1 and D2 is coming from B1. Applying the transfer function, gives out as D2 and D3 because D3 was generated and D1 was killed. B3 is in merges from both B1 and B2 path. In pass 2, we recheck block from whose predecessor changed. When nothing changes between iterations, we have reached the fixed. The result. At definition D4, the use of A in C equal to A plus B. The reaching definition for A are either D1 A equal to 3 or D3 A equal to 7. Depending on which branch was taken, the compiler cannot replace A with a constant here, but it doesn't know the complete set of possible values. If D3 didn't exist and D1 was the only reaching definition, constant propagation would fire. Now advanced optimization via DFA. Beyond the classical 6 optimization, DFA powers several advanced compiler techniques. Register allocation. Every variable needs to live somewhere, either in fast CPU register or in slow memory. Live variable analysis tells us which variable are simultaneously live, meaning active at the same time. Variables that are never live simultaneously can share a register. This is formalized as a graph coloring problem on the interface graph. Better allocation means fewer expensive memory spills and faster execution. Alias analysis. In languages like C and C++, pointers complicate everything. Two pointers might or might not refer to the same memory location. This analysis, a form of DFA, determines may alias pairs. These two pointers could point to the same thing versus must alias pair. They definitely do. Without this, the compiler must conservatively assume everything might alias, crippling other optimizations. Inter-procedure analysis across function call boundaries. Normal DFA stops at function call. Inter-procedural DFA uses the graph call to propagate facts between caller and callee. Context-sensitive version tracks separate facts per calling context. More precise but exponentially more expensive. Merges all callers, cheaper but less precise. Finally, SSA form, static single assignment, transforms the program so every variable is assigned exactly once, with pi functions at merge points to select between versions. This makes DFA space instead of iterating over all blocks. We only need to follow def use chains. This is why GCC, LLVM, and JVM, JIT compilers all use SSA internally. Summary and key takeaways. Let's close these six things to remember from this video. 1. DFA statically tracks how data value propagates through a program control flow graphs. No runtime needed. And the second, there are four classical problems: reaching definitions, live variables, available expressions, and very busy expressions, each differing in different and meet operators. And the third, the solution framework is always the same: transfer function plus a meet operator plus fixed point iteration. 4. DFA powers dead code elimination, constant propagation, CSE, LICM, copy propagation, and register allocation. The core of what makes optimization compiler fast. And the 5. SSA form combined with past DFA analysis dramatically speed up modern compiler analysis process. This is why all major compilers uses it. 6. Interprocedural and alias aware DFA extends analysis precision across function call boundaries and pointers heavy code. The closing thought of this deck says it's perfectly. Data flow analysis transfers the compiler from a translator into an intelligent optimizer. That's the magic. You write code for humans to read, and the compiler uses DFA to run it into code that machine runs efficiently. Thanks for watching. If you found